Let's assume you can do that. Then what's next?
So
just assume we tolerate the mass error here.
Yes, a good physicist never lets the mathematics slow it down.
Another good point also. I like it. Okay. Well, here is inherent to the question. Okay. Everybody will stop you at this point.
Here, spatial length is limited. How do you use Laplace transform? Time.
Yeah.
Time
That's another good point. Another good
infinite.
point.
Infinite. But the spatial length is finite. How do you use again? It's transform again. This is another. Yeah, you use the Fourier Laplace transform. You know, the space length is very finite. It's not. It's only infinite.
Yeah, and actually you have the same kind of problem. One is you have a slow variation in time, you have this rapid fluctuation in time, that's the Laplace transform, and then you have this oscillation in space, and then you have a slow spatial variation that the oscillation in space is on, and you have to disconnect those two. It's the same kind of problem in both space and time.
Okay. Okay, I assume if you in the UCLA IPAM, you will invite more criticism like this. Okay, get ready for it. You got a poster and just print it. I say be careful. Okay, here you will invite. So try to learn how to resolve this and in some other ways. You jump to this point, and I think
maybe I can skip this way and use another method to get this result.
there are some inherent problems that need to be resolved.
Yeah.
I told you many times, so you can't say, because other people said it in this way, I do the same thing. No.
Well, I think the cleanest way to resolve it is, on the left you have the time derivative, and you assume two time scales, t1 plus eta t2, and eta is a small parameter, and you do an expansion in that small parameter. Then you do the same spatial resolution on the right, and you keep them both to the first order, and what you'll have for the C down there is the term you have there, and then a correction of order those parameters in space and time.
Okay.
I think that's the cleanest way. And it may turn out that those corrections are stronger than the term you kept, but that's another matter.
That's to solve the mathematical difficulty here.
Yeah.
So, but if you do CTRW, possibly you do this way, and it may happen to be the same. So.
In the CTRW models, I will not use this method
So
because the aim of I use this method is that we can get the expression of the mean square experiment.
Okay.
So there are also other people have used this method, so I use this method.
You cannot say that you can mimic this kind of divergent variance type. Look like this. You have noisy and noisier tail. You can mimic this, and so that your Laplace transformation is correct. That's not right. Okay, don't. I understand that you try to capture that kind of divergent behavior of the variance, and like this, and you want to capture and using a variable order, and according to your numeric technique, and happen to capture it. So then that mass equation is right. No, it is not. Still, I am suspicious about it. Okay. Keep going and see what's next.
Okay, here is we use a different frequency of the noise, have different behaviors. The right line B represents the larger frequency noise. Here we make a comparison of the DO model and the wheel models. We found the DO models can depict the cupping process. Meanwhile, the wheel models depict the evolution process. At the same time, the DO model and wheel model cannot be changed to each other because they are totally different.
So distributed order versus a variable order.
Yeah. Based on the above several models, we propose a generalized distributed variable order models. So in these models, the it includes other potentials models. After further research, I will make the application of the fractional models. The first, I will use it to analysis to experimental data of the bacterial metastasis. We can see the first picture is tricking of bacteria. Second is for an example of one bacteria and migrant with the time, and looks like the random walk. So I will use this the fractional model to depict this phenomena. Others, if we consider the models, only we know the interval of the derivative orders. For example, alpha 0 to alpha maximals. So in these conditions, we can use the fuzzy orders to depict this diffusion process. If we consider more complex diffusion process, we can say in the first system, we know the order, derivative order of the first system, and the output is the derivative order of the second system. It's more normal in the physics, so in the future, I will consider this system. Okay, thank you for your attention.
Oh, good. So, thank you very much.